In this video, we just want to focus on curve sketching. So I'm going to outline a procedure here, and then we're going to do an example. So the first thing you should do is you should identify the domain and any symmetries. Second, you should identify any asymptotes. The third thing you should do is find the intervals of increase or decrease. So find where your function is increasing or decreasing. And you do this by finding the first derivative and evaluating the first derivative on intervals separated by our critical values. That's something we did in a previous video. For the fourth thing is we want to find intervals of concavity. So this is a very similar thing to part 3, except we're going to do essentially the same thing but on the second derivative. And when we find intervals of concavity, that's going to help us find points of inflection via the second derivative. Using these first two things, these previous two things, number 3 and 4, we can identify local maxes and mins. And then finally, put all of this information together to plot or sketch our curve. In fact, that's a better word. Let's call it sketch. All right. So we're just going to run through an easy example here for our first example. We're going to sketch the graph f of x is equal to x to the fourth minus 4x cubed plus 10. Okay, the first thing we want to do is identify the domain and any symmetries. All right, this is a quartic polynomial. And this thing in here is positive, leading coefficient is positive, which tells us we're going to, the fact that this is positive really just tells us what our end behavior is. That more tells us our identifying any asymptotes. We know that there's no asymptotes here. So that was more of part 2. But going back to part 1, identifying the domain is everything here because it's a polynomial. So the domain is all of R, the whole real line. So whatever you want to use, you can use this R here to mean the whole real line, or we can just write our interval notation from negative infinity to positive infinity. The second thing is going to identify any asymptotes. No asymptotes, horizontal or vertical. The third thing we want to do is find intervals of increase and decrease. We do that by finding the first derivative. All right, so f prime of x is equal to 4x cubed minus 12x squared. And the 10 goes to 0. So from here, we can factor out a 4x squared, and we get x minus 3. And so we see two critical values, c equals 0 and c equals positive 3. So what this is going to do is it's going to separate our domain into 3 intervals for increasing and decreasing. So the first thing we want to do is we will write out those intervals. So from negative infinity to 0, from 0 to 3, and from 3 to infinity. Oops, sorry. What am I even doing here? Negative infinity to 0. I don't know what I'm writing down right now. Okay, there we go. Better. And how do we tell this? Well, we just write our factors out here, and then we can determine what the derivative is doing, and that'll tell us what the original function is doing. Right? Pick a value between negative infinity and 0. Let's just pick like -5. We put it in here. This is definitely positive. -5 minus 3, that's a negative. Which tells us, if we just plugged it into our original derivative here, this whole thing is negative. The derivative is negative. Which tells us our function is decreasing on that interval. And then our function is... well, let's see. Plug in 1 or 2, or anything really between 0 and 3, but 1 or 2 is is the best choice. So let's plug in 1, we get a positive. 1 minus 3 is negative. So this is again negative. So our function is decreasing. All right. And then we have, let's plug in 5 here. This is positive, so that makes the whole thing positive. So our function is increasing. Okay. Now there's a few ways to determine local max or min. If the function changes from decreasing to increasing, that means we were going down, and then if this function starts going up, that tells us we have a minimum at 3, and whatever that value is there is just we got to plug in 3 into the original function right here. So 3 to the 4th is 81 minus 27 times 4 is what, 108 plus 10, so we get -27 plus 10 is -17. So 3, -17 is a local minimum. Since our function goes from decreasing to decreasing here, we don't have a maximum or minimum at 0. All right, let's keep going. Let's just use a new page. All right, so now we want to find intervals of concavity. Our derivative, f prime of x, was 4x cubed minus 12x squared. And so our second derivative is, let's see, 12x squared minus 24x. We can factor out a 12x here, and we get x minus 12. Sorry, that's not true at all. X minus 2. I'm making so many mistakes on this video. X minus 2. All right, which tells us we again have potential critical value, or we do have critical values here at 0 and 2. Because that's what makes our derivative, our second derivative, 0. And this gives us intervals of -infinity to 0, 0 to 2, and 2 to infinity. And our function is, let's look at our factors. Our factors are 12x and x minus 2. This is our second derivative, and what does that tell us about our original function? So let's see, plug in -3, this is a negative, this is a negative, so this is up. If the second derivative is positive, then that tells us our original function is concave up. Plug in 1 in between 0 and 2, we get a positive, we get a negative here. This means that the second derivative is negative, because we just multiply, right? Multiplying these factors to get the whole thing. So this is negative, which tells us our function is concave down. And then we have, let's see here, plug in 3 or 5 or 10 or 100 billion, doesn't matter. We get a positive, so this is, the whole thing is positive. So this is concave up. Anytime we switch from concave up to down or down to up, we have a point of inflection. So we have a point of inflection at 0, 10. And we have a point of inflection at 2, and then we got to plug in 2 into our original function. Our original function is x to the 4th minus 4x cubed plus 10. So real quick, what is that? Let's see, this is 16 minus 32 plus 10. That's negative 16 plus 10 is negative 6. So we get 2, negative 6 for our point of inflection here. Now let's put all of that information together, right? We want to graph our function. We have a minimum at 3, negative 17. So 1, 2, 3, and then negative 17, which we'll say is down here. We're just getting a quick sketch. We have a point of inflection at 2, negative 6. Let's just put that about here. And, oops, sorry. And we have another point of inflection at 0, 10. So we can put that about here. And now, those are the only critical values we had between the second and first derivative. We're at 0, 2, and 3, right? We got the 0 and 3 from the first derivative, and we got the 0 and 2 from the second derivative. So these are the essentially the breakpoints for each of our intervals. So we have 1, 2, 3, 4 entire intervals here that we want to see what the function is doing. First off, as x goes to negative infinity, the function shoots off upward, right? So we were talking about, when we talked about asymptotes earlier, we said there's no asymptotes, and that's because the function shoots off upward. Moreover, from negative infinity to 0, our second derivative tells us we are concave up. Our first derivative, if we bring that back into focus here, our first derivative from negative infinity to 0 is decreasing. So we want a decreasing but concave up function. Reminder, that means the function looks like that on that interval. Between 0 and 2, we are concave down, and the function is decreasing. Right? If we look back at our first derivative information, we said we were decreasing on the interval from 0 to 2. In fact, from 0 to 3, but that includes 0 to 2. And the second derivative tells us our function is concave down. So what does that look like? That looks like this. All right. And then from 2 to 3, we have decreasing still, but concave up, which means the function goes back to looking like this. I could draw a little better here. Sorry. If you mess up on drawing, just make the line thicker. That's how you fix it. And then, if we're going from 3 to infinity, we are concave up on that interval, and the function is increasing. So we got a pretty detailed sketch for what our function should look like, given all of that information. All right, and that'll complete our first example for curve sketching. We'll go over several more throughout the week in class. All right, that'll end this video here.